So first, a little bit about me. My name is Claudio Orlandi. I am an associate professor here at the Department of Computer Science, and I've been here for the last 13 years, maybe, working with cryptography, doing research in the security and efficiency of cryptographic protocols. So I really like and enjoy this part of the course. Let me start by saying that what we're going to cover about cryptography in this course is quite the basic material. So let's start with the topic of the day. So today we're going to talk about confidentiality, introduction, and secret key cryptography. So the problem that we're going to solve with cryptography is the following. In an ideal world, communication proceeds like it does in this slide. You have some sender, Alice, here, who sends a message to Bob. And Alice and Bob are the only people in the universe. So this message that starts from Alice and goes to Bob is only seen by Alice and Bob. Unfortunately, the real world is a bit more complicated than that. And when you communicate, for instance, on the internet, when you send a packet to someone else, this is not simply sent by magic from you to the receiver, but it goes to multiple hops over the internet. And maybe some of these hops, maybe some of the people controlling the hops over the internet are malicious and are interested in listening to your traffic. This is not a dream scenario. This is not being paranoid. We know that there are criminals, governments, agencies that are interested in listening to people traffic for all sorts of different reasons. So when you communicate on the internet, it looks much more like this. You have Alice here who sends a message. This message is first seen by this pirate, this adversary. And then this pirate, this adversary, can send the message forward to Bob. And note here that the color of the message has changed a little bit because the adversary might be able to change the content of the message. So the final goal of the next couple of weeks is going to be secure communication. We're going to want to allow Alice and Bob here on the picture to communicate securely. And what do we mean when we say securely? It doesn't make sense to talk about security unless you first define what security means. So when we talk about security, we're going to talk about two different properties, both very important. So as you can see here, the message that Alice sends is encrypted. It looks encrypted. There is like some kind of lock. The lock shows that the pirate here cannot read the message. The pirate gets nothing out of it. Not only that's true, but it's also true that the message that comes out here from the pirate to Bob, it's exactly the same as the message that Alice sent. So those two properties are two orthogonal properties. They're both very important when we talk about secure communication. And we're going to see this week and next week tools to solve the two problems independently. So again, this week we are going to focus on confidentiality. What is confidentiality? Confidentiality, or maybe secrecy if you want, is the cryptographic goal of having the message that goes from Alice to Bob being unreadable by the pirate, by the adversary. As you can see from the picture, the message goes from Alice to Bob. The pirate cannot read anything, yet confidentiality doesn't on its own guarantees that the pirate cannot change the message. So the message, when you use confidentiality techniques, you're not automatically guaranteed that Bob will receive the right message. The other tool, the other goal, which we'll look at, is authenticity, sometimes called integrity. This is what we look at next week. In authenticity or integrity, what you want is that the adversary, the pirate, cannot change the value of the message. So here you can see that the message comes from Alice to Bob. The adversary might be able to see it. Having authenticity doesn't necessarily imply that the adversary doesn't see the message, but it implies that the adversary cannot change the message. Note that sometimes, we're going to talk about that next week, but note that sometimes there is some kind of duality introduced, whether it's message integrity, message authenticity, or sender integrity, sender authenticity. So do we care about the content of the message being valid, or do we care about Bob knowing who the message comes from? So in fact, these two properties are really, really just the same, as we're going to see next week. The goal of confidentiality is that information should not leak to unauthorized people. The adversary, or the threat model of confidentiality, is someone who can read from the channel on which the parties are communicating. And the solution, the security mechanism you're going to use, is secret or public key encryption. Next week, we're going to look at authenticity. The goal of authenticity is that, or the security policy is that the information should not be modified by unauthorized people. The adversary, when we talk about authenticity, is someone who can write on the channel. And the solution we're going to see is secret or public key authentication, also known as MAC or signature schemes. Once again, a recap of what we're going to see in these 2 weeks. Here is the taxonomy. We're going to talk about confidentiality this week, authenticity next week, and we're going to see different solutions. The solutions we're going to look at can be divided into 2 further ways. One way of dividing the solutions we're going to look at is whether the solutions we're going to look at guarantee unconditional security or computational security. So unconditional security means that the security should hold against any adversary, regardless of what their computing power is. Whereas computational security means that the security only holds against adversaries who have limited computing power. So what do I mean here by limited? I mean limited by what we believe that is the maximum possible computational power on the planet, and much more. So computational security doesn't mean that if someone buys a bigger computer, they can break it. It just means that there is a theoretical possibility of breaking it if someone has a amount of computing power which is beyond what it's believed to be feasible today. Whereas unconditional security holds against any, doesn't make any such assumption on the computational resources of the adversary. Another way of dividing solutions for confidentiality and authenticity is whether they are secret key or public key based. So in a secret key system, you will have that the recipient and the sender, they share the same key, they have the same key material, whereas public key cryptography is some kind of much more, if you want, magical solution in which the keys that the sender and the receiver holds are different, and in fact, one of the key can be made public, and yet, even if this key is made public, the adversary cannot break the system. So this week, we're going to look at one-time pad as a solution for unconditional security, and stream cipher, block cipher, and mode of operation. The 2 things together is what typically is the first lecture. And then in the second lecture, we're going to look at RSA encryption and padding OAP. So let's look at how encryption scheme for secret key works. So this picture is a bit, might look a bit overwhelming, and there are a lot of elements. So let's try to decode them one by one. So let's start with from the left. Here we have Alice, which is our sender. She receives a message from somewhere. Using the language of the book, the message comes from the environment or from some other process. So the sender in this symmetric encryption scheme receives this message and wants to encrypt it. How do we encrypt the message? We encrypt the message using some key. This key K, which is generated by some key generation algorithm. Who runs this key generation algorithm, and now do Alice and Bob both get this key? This is going to be the topic of another week where we're going to talk about key management. For now, let's assume that at the beginning of time, someone runs this key generation algorithm and provides Alice and Bob with a key. In practice, you could imagine Alice and Bob meeting in some room and running this algorithm together. Usually, this algorithm is actually very simple to run. Usually, this algorithm just samples a uniformly random bit string. So just a bunch of zeros and one, completely at random and uniformly independent. So you could imagine Alice and Bob meeting in a room and just starting flipping coins until they have enough bits to get this key. And then after they leave each other, they each go where they want, they both bring this key with them. So this example with flipping bits on keys is not so crazy as you might imagine. In the old days, military encryption machines used key material which was printed on books, and these books were printed by the secret agency, would then distribute these books to the ship that was sailing and had to encrypt the communication to mainland, and the people receiving the messages on mainland, they would have the book with the other part of the key. So this is not such a far-fetched example. So now Alice gets this message and this key, runs the encryption algorithm ENC, and produces something that we call a ciphertext, C. As you can see here, C is in a green bubble, and everything which is green on the slides is seen by the adversary, whereas everything which is orange or red should not be seen by the adversary. So the adversary is allowed to see this ciphertext C. As you can see, this communication happens over an authenticated channel. which leaks the ciphertext C to the adversary. Since the channel is already authenticated, and how do we do the authenticated channel? We'll see it in the next week. The ciphertext is received by Bob without being modified, and now Bob can decrypt the message using decrypt the ciphertext using the key and receive the message back. Okay, so this is how symmetric key encryption is used. The first example of symmetric key encryption that we are going to look at is one-time pad. So what is one-time pad? One-time pad is the one and pretty much only example we have of an unconditional secure encryption scheme. So this is the only encryption scheme we have which is secure no matter how much power the adversary has, how much computational power the adversary has. So even if tomorrow, someone discovers a computer so huge that can make computation which is unfeasible today, still one-time pad would be secure. So how does one-time pad work? So one-time pad works on strings of bits. I'm gonna pause the slides and try to write a little bit on the whiteboard behind me, and I hope that you can see this on the video. So let's pause the sharing of the screen, and let's go on the board. So in one-time pad, you start with a key. A key is just a vector of bits, which in the slides has length t. So this is just a vector of random bits, 0, 1, 1, 0, and something else. In one-time pad, the message is to a vector of bits. The message is, however, not random, so this is random. The message is not random. This is what you send. So this was is the message you want to send. It could be, for instance, 1, 0, 1, 0, and something else. And then by doing some manipulation of the key with the message, you obtain the ciphertext C. So how do you compute the ciphertext from the message and the key? The way you do this is by doing the XOR, or the exclusive OR, of the key with the message. The XOR function is the function that takes 2 bits and maps them into a third bit. And now I conveniently chose the bit of the key and the bit of the messages such that I can compute all 4 possibilities for XOR. So 0 XOR 0 gives 0. 0 XOR 1 gives 1. 1 XOR 0 also gives 1. The function is symmetric. Whereas 1 XOR 1 gives 0. Another way of talking about XOR is addition modulo 2. So 0 plus 0 is 0. You're used to that. 0 plus 1 is 1. That's the natural addition rule. Whereas 1 plus 1 gives 0 because 1 plus 1 is equal to 2. And if you take modulo 2, you get like 0. So this is how one-time pad works. So let me go back to the slide. And let's start sharing the slide again. So the message is retrieved by computing the XOR, the exclusive OR of the key with the ciphertext. And the nice thing of XOR function, and now I want to go back to the board, is that if you XOR something to itself, it goes away. So let's stop the sharing again and let's go back to the board. So if I now take this ciphertext, so let's do this here. If I take the ciphertext, here, which is 1, 1, 0, 0, and I XOR it together with the key, and my key here was 0, 1, 1, 0, and something else. I'm going to retrieve back the message. Since if I do 1 XOR 1, 1 XOR 0, well, that's 1. Oh, that matches my first bit. And 1 XOR 1 is 0. That matches my bit. And 0 XOR 1 is 1. And 0 XOR 0 is 0. So in general, I mean, I can write this, of course, more compactly. I'm going to get the encryption example. So the ciphertext is the message XOR the key. The message is obtained by getting the ciphertext XOR the key. since the ciphertext itself is the message XOR the key, but anything XOR itself is 0, so you get like the message. Great. Let me stay at the board a little bit more because we want to prove that one-time pad is perfectly secure. So what does it mean that one-time pad is perfectly secure? So one-time pad is perfectly secure, meaning that when you use one-time pad, the ciphertext is a completely uniformly random string, which is completely independent of the message. Regardless of which message you're encrypting, the ciphertext will always look like a completely uniform random string. So for simplicity, let's look at the case where the ciphertext is only 1 bit, and then this generalizes to a message of multiple bits, and you can find the proof in the book. So let's look at what is the probability that in one-time pad, if you have a ciphertext which is only 1 bit, what is the probability that this bit is equal to 0? Of course, if I can prove that the probability that C is equal to 0 is 1/2, then since there are only 2 possibilities, C0, C equal 1, then the probability that C equal 1 always also going to be 1/2. And if something is 0 or 1 with probability 1/2, then it's uniformly random and contains no information about the message. Okay, so what is the probability that this ciphertext is equal to 0? Well, that is the probability that the message happened to be 0 and that the key happened to be 0, because 0 XOR 0 gives you 0, plus the probability that the message was 1 and that the key was 1. Because 1 plus 1, or 1 XOR 1 gives 0 because of the modulo 2 nature of the exclusive OR. But now we're in luck because what is, so now we have a probability here, which is the probability of 2 events. And normally when you have probability of multiple events, you need to look at it's more complicated to compute, but in this case, it's very easy because I told you that the key is sampled uniformly at random and independent of the message. So these 2 events are independent. So the probability that the message is equal to 0 and the key is equal to 0 is simply the product of the 2 probabilities. So this is equal to the probability that the message is 0 times the probability that the key is equal to 0. Plus, similarly here, that's the probability that the message is equal to 1 times the probability that the key was 1. But I also told you that the key was sampled uniformly at random. So both of these probabilities are in fact just 1/2. So I get that this is equal to the probability that m is equal to 0 times 1/2 plus the probability that m is equal to 1 times 1/2. And now I'm pretty much there. Let me rewrite this like this. So I put the 1/2 in front, and then I have the probability. Now I have 1/2 times the probability the message is equal to 0 plus the probability that the message is equal to 1. But what is this? We don't control the message. We don't know where the message comes from. So we don't know if the message, what is the probability the message is 0 versus the probability that the message is 1. But we know that the message can only be 0 or 1. So the probability that the message is 0 plus the probability that the message is 1 is 1. There are no other possibilities. So this is in fact just 1/2, which proves our claim that one-time pad is produces uniformly random, perfectly uniformly random ciphertext independent of the message. Okay, so now let's go back to the screen. The other thing we want to say about one-time pad is that one-time pad is optimal for perfect secrecy. What does it mean? It means that if tomorrow someone comes to you and says, and these people come, by the way, all the time. I mean, if you're a cryptographer working at university, you often get emails from people saying, hey, I discovered a new encryption scheme, which is better than one-time pad. So this is completely impossible. So one-time pad is optimal for perfect secrecy. It's the best and pretty much the only perfectly secure encryption scheme that you can have. So we'll see a reason for that. So the main, so if you go back to the description of one-time pad, so let's see 2 things. First, why is it called one-time pad? It's called one-time pad because the proof of security, which I made on the board behind me, only works if the key is only used once. So that means that if you reuse the same key to encrypt multiple messages, one-time pad is not secure. And in fact, there are exercises in the book where you will see exactly why it's not secure. So that's why it's called one-time pad. It's called one-time pad because the key has to be used only once, and the key is as long as the message is. Right. So this, of course, is also the main issue with one-time pad, which means that the keys are insanely large. So if you, when you connect to a website on the internet, you might download megabytes and megabytes of content. If you want this content to be encrypted, you will need to have pre-share with this website a megabyte long string of bits. And this is very impractical, right? How do you get all these key materials? Before I mentioned these books, right? And I mean, where you could maybe have a lot of random numbers that you can use from now to the end of the day, but that's just really a lot of random bits that you need. So one-time pad, it's very impractical, and it's not used in practice because of this requirement that the key can only be used once, and the key has to be as long as the message. Unfortunately, we're going to see here that this is inherent, and there is no encryption scheme that can do better than this, unless if you want perfect secrecy, you cannot do better than this. So what does perfect secrecy means? Perfect secrecy means that the ciphertext is independent of the plain text. And theorem 5.2 in the book shows the following thing. If you say that big M is the number of possible plain texts, and big C is the number of possible ciphertexts, and big K is the number of possible keys you have in a system, then perfect secrecy implies that the number of possible keys K is larger than the number of possible ciphertexts C, which is in turn larger than or equal than the number of possible messages M. So in one-time pad, we had that these three numbers were actually exactly the same. So the number of possible messages M is exactly the number of possible ciphertexts, which is exactly the number of possible keys. They're all just bit strings of the same length. And if you so any other encryption scheme which has perfect secrecy either performs as well as one-time pad or worse. Right. So let's see why this is the case. So I'm going to go back at the board. So let's draw here a set of all possible ciphertexts, of all possible messages M, and here a set of possible ciphertext C. So the first thing we want to prove, sorry for the chair, is that the number of possible ciphertexts must be larger or equal than the number of possible keys. And why is this the case? So that means that for every message I have here, there must be a corresponding ciphertext there. For this message here, there must be a ciphertext there. Could it be the case that there are two messages? Let's make it here red. There is another message that goes to the same ciphertext. Well, that cannot be. Why? Because if you had two messages that went into the same ciphertext, then the encryption would not work. Once you have this ciphertext, how would you know whether to go to this message or that message? So that means that cannot be more than one message that maps into the same ciphertext. Therefore, the number of ciphertexts is at least the number of messages. And that was the first part of the claim. In the second part of the claim, we want to say that the number of possible keys is also larger or equal than the number of possible ciphertexts. And let's see why this is the case. So let's now fix some message M. We just fix a message. Let's take a message and let's fix this message. We now argue that for every possible ciphertext that you have in this set, there must exist a key that maps this message into that particular ciphertext. Let's suppose that there was one ciphertext here which is not reachable from this message. So there is no way of going from this message to this ciphertext. There is no key that brings this message into this ciphertext. This is B1, B2, B3. Every ciphertext here has a key that maps this message into that particular ciphertext. But this ciphertext doesn't have a key that brings this message into that ciphertext. So can this be the case? No, it can't. Why? Because the encryption scheme has perfect secrecy. So if this was not the case, if an adversary sees this ciphertext, they would already be able to exclude that this was the message that was encrypted. So they will be able to learn some information about the message. It's not a lot of information, arguably. You only know that the message is not this particular one. It can be any other one, but it's not this particular one. But this is enough to break perfect secrecy. So that's the proof of the second part of the claims. So let's go back to the board, to the slides. The consequence of the theorem we just saw is that you should never, ever reuse one-time pad keys. In the book, you have this example with this picture. Here on the left-hand side, you have the plain text image. There is a picture in black and white. Every pixel is either 0 or 1, black or white. And in the middle, you have a picture which has been produced by encrypting this picture with one-time pad. Of course, this picture is not a proof, but this picture shows that, the picture is supposed to make you think about the fact that this is completely random. There is no structure of the original picture left in here. The right image, on the other hand, is an encryption of this image where every row was encrypted using the same key. So I've reused the same key to encrypt every single row. And as you can see some structure in this picture. I hope that the video shows this structure, but I mean, you can detect, for instance, that this area is white, or at least that all the pixel in a majority of the pixel in these rows are either white or black, which means that they were all of the same color in the original picture. You can see some shape of the head here. So a lot of information leaks by reusing, because of the reuse of the key.